Welcome back to Calculus. Today we're looking at section 5.5, indefinite integrals and substitution. So the thing with indefinite integrals is we don't have those limits of integration, so we're not going to see the little numbers at the top and the bottom of our integration symbol. And importantly, that means that we're going to need a constant when we integrate. We're going to have that plus c because we don't know which function it actually is. It could be any of many, an infinite number of functions, really. All right, so here's how this is going to work. We're going to learn substitution here. That's really the big thing. It works this way. It is a theorem. I didn't write down the theorem number, but here we go. If u equal to g of x is a differentiable function, and we have the integral of f of g of x, okay, so there's an inside piece, times the derivative of g of x dx. Okay, so importantly, what we're looking for here is we're going to be looking for something that we can do some substitution with. We're going to replace that g of x with a u, but, well, we get the integral of f of u du. And so what we're going to do here is this is really working the chain rule backwards, right? We learned the chain rule when we did derivatives, and it was a way of dealing with functions that had another function embedded inside. Well, substitution is just recognizing that, hey, if we can find an inside function, and its derivative is sitting out there next to it, then we might have something going here where we can find our integral. So I have some steps that we're going to follow for these problems. We're going to first substitute. We're going to plug in u for g of x, that inside piece, and we're going to use du, where du is equal to du dx times dx, or really it's just g prime of x dx. And once we have that, we're going to integrate, but we get to integrate with respect to u, which is going to be way simpler looking than the problems will start out. And then we can, once we do that, we replace the u with g of x, and don't forget your c because we are looking at indefinite integrals here. All right, so let's dive in. I have several examples, and it'll be fun. Okay, so here's my first example using substitution. I want the indefinite integral of x cubed plus x, all raised to the 5th power, times 3x squared plus 1 dx. So what we're looking for is we're looking to make a substitution here where the thing that we replaced with a u has a derivative that's already in the problem. That would be great. And ideally that's what happens. It doesn't always quite work out and we have to get a little creative, but this one's going to be relatively straightforward. So easy, or not easy, but the best place to go looking is at the most complicated part of the problem. So I have a polynomial raised to a power. The inside piece here, x cubed plus x, seems like a wonderful candidate to be substituted. Okay, and so I'm going to try it. If the substitution doesn't work, we'll go back to the drawing board. But it's going to work here. So let's set u to be the x cubed plus x. If we take its derivative, we get 3x squared plus 1. And don't forget, we're really using a chain rule here because we're taking the derivative of u with respect to x. So we need a dx at the end. And that's useful because look at what we actually have here. We have 3x squared plus 1 dx. And so that's just going to be my du. So it looks like we have what we want. I'm going to put u in for x cubed plus x. There's my u to the 5th. And I'm going to replace all that mess with du. And that integral looks pretty nice, right? The integral of u to the 5th? Yeah, please, that's great. So we raise our power by 1. We divide by the power, right? We raise it and divide. And don't forget your plus c. And then the only thing left to do is to substitute back. We want x's here. We started with x. We want to end up with x. So I just bring back the x cubed plus x in place of the u. And we're all set. So that one wasn't too bad. We're going to see a couple of, I have several more examples. Looks like maybe 4. I have 4 more examples. And some of them are definitely going to be harder than that one was. So let's take a look at the next one. Okay, so here's my next example. I want the indefinite integral of the square root of 3x minus 7 dx. So again, this is a great candidate for a substitution. I'm going to let u be the 3x minus 7, and which means that du is 3 dx. Now, unfortunately, when I look at this integral, I can see where I'm going to put the u in, and you can see I changed it to a 1/2 power because I like integrating with the powers better than the radical. But unfortunately, I have dx, I don't have 3dx. So we can't just go and plug in du instead. We have a piece here that's not in our problem. All we have to do is just solve for dx, right? We want to substitute and get rid of dx. So if I do that, I can divide both sides by 3 or multiply by a third, and I get the dx is the same as 1/3 du. And so I plug in 1/3 du in place of that dx. And so when I do that, I brought the 1/3 out front of the integral, because you can always pull that constant out as long as it's multiplication. So now I just have the integral of u to the 1/2 du. I raise the power by 1 to get 3/2. I multiply by the reciprocal, because that's the same as dividing. And then I clean up the mess. 1/3 times 2/3 gives me 2/9. And I plug in the 3x minus 7 back in for u. And of course, I have my c here at the end. There we go. Let's do another one. All right, this example is in many ways really similar to the last one. I have the integral of cosine of 5 theta plus 9 d theta. So we'll see the similarities here in just a second. U is going to be the 5 theta plus 9. Again, I'm making it that inside piece. I take its derivative, and I get 5 d theta. Right? The derivative of 5 theta is 5, and we get a d theta. Again, just like the last one, this problem doesn't have a 5 in it. So we can't do the substitution as it's written. We have to divide both sides by 5 so that I can swap out d theta for 1/5 du. So I do that, and I put the 1/5 in front of the integral because I like it there. You could leave it inside here, but I brought it out front. The integral of cosine is sine. Watch out for the negative and positive signs here, right? The derivative of cosine is negative sine, but the antiderivative of cosine is just sine. So I get 1/5 sine u plus c, again, not forgetting our c because we do have an indefinite integral. And then I just replace u with the 5 theta plus 9. So you can see a lot of these are really pretty nice. Let's do a couple that are maybe just a bit messier. Okay, I lied. This one isn't really any messier, but the next one will be, I promise. So I have the indefinite integral of x squared e to the x cubed dx. Again, I'm going and looking for the most complicated bit, which is the e to the power. That's where I want to try and put something in for u. And it works out nice because if u is x cubed, du is 3x squared dx. And that's great because we have x squared, so this substitution will allow us to get rid of the x squared and the dx. But we still don't have that 3. So just like on the last two examples, I'm multiplying both sides by a third, dividing by 3, however you want to think about that. And I'm going to swap x squared dx for 1/3 du. Okay, very nice substitution. So now I have, and again, just like on the last one, I put the 1/3 in front of the integral because I like it there. It's out of the way. Now I have e to the u because the x squared and dx both turned into the du. So the antiderivative of e to the u is just e to the u, so I get 1/3 e to the u plus c, and then go back and replace the u with x cubed, and we are all set. So there we go. That's that example. I have one more. It's definitely the messiest of the bunch, so buckle up. All right, so for my last example, I want the indefinite integral of x times the square root of 2x plus 1 dx. So we're going to start this one just like we would any of the others, and there's definitely a problem with this one, and we'll see it. You can actually kind of see some of it written out here, but let's walk through what happens here. So I set the inside of the square root equal to u, so the u is 2x plus 1, which means that du is 2dx. And immediately we get two problems. First, and the easiest one is, there's no 2 in here, right? There's a 2 inside, but that's part of u. There's no 2, so I have to divide both sides by 2, so dx will be 1/2 du. That's not the problem. We've seen that before. That's happened to us. The problem is really this extra x right here, right? We have an extra x that we can't substitute out using any of the stuff we've done before. But here's the thing. We know that u is equal to 2x plus 1, which means we can solve this for x to get a substitution for that x. Okay, so we know that this inside piece is u. I just want to solve that inside piece. I want to get x by itself there so I can plug that in for x. And if I do that, I subtract the 1 to get u minus 1 is 2x. I divide by 2, so I get u minus 1 over 2 is x. And that's what I'm going to put right here for that x. So you can see I have my integral going over here. I put that 1/2 out front. A lot of pieces here. Don't lose any of them. If you lose something, it's going to fall apart on you. So the half I put out front. Here's where I put the u minus 1 over 2 in for x. And then I rewrote this as u to the 1/2 instead of the square root of u du. Now, what makes this a little bit nicer is I can actually bring that 2 out. This is like a half times u minus 1. And since we can always bring out things that we're multiplying, let's just bring that half out. So a half on the outside times the half on the inside gives me the 1/4. And so now I have 1/4 times the integral of u minus 1 times u to the half du. Let's make that look a little bit more like a u. There we go. And so then I just distribute my u to the 1/2. So I get 1/4 times the integral of u to the 3/2, right? 1 plus a half is 3/2, minus u to the 1/2 du. And now I can integrate. I'm keeping the 1/4 in front. I'm going to mess around with the stuff on the inside here. I raise the power by 1, which makes it 5/2, and multiply by its reciprocal. I raise the power by 1, which makes it 3/2, and multiply by its reciprocal. There's my plus c at the end, and all that's left is to clean up the mess. So you can see I plugged in the 2x plus 1 here for the u's, and more than that, I also multiplied the 1/4 times 2/5, which gave me 1/10, and 1/4 times 2/3, which gave me 1/6. So there's our indefinite integral for that one. That is a mess. Spend some time with that one because it's got some really neat little tricks in it that you're gonna need as you go through all of this substitution. So thanks for coming and watching the video. Have a wonderful day.